Let's take what we just learned about symmetric matrices and apply it to this particular example. So we have a matrix A. Notice that matrix A is a symmetric matrix. Each row of A is equal to the corresponding column of A and vice versa, right? Which means, based on the theorem we just proved, that for any symmetric matrix, like matrix A, there is a way to diagonalize it using some orthogonal matrix Q, all right? So normally when we diagonalize a matrix, there's some matrix P, so that P inverse AP is equal to D. But in this situation, we're going to use an orthogonal matrix Q in place of P, and the inverse of Q is just its transpose. So that's the plan. Now, to diagonalize a matrix, we need the eigenvalues and the eigenvectors of the matrix. Remember, the entries along the main diagonal of the diagonal matrix are the eigenvalues of A, and then the columns of matrix Q here are going to be eigenvectors of matrix A. All right. So first step, we need to find the eigenvalues and eigenvectors of matrix A. Now we know how to do that by hand, but to save us a little bit of time, let's use the computer. So first row of A is 0, 2, 2. Second row of matrix A is 2, 1, 0. And last row of matrix A is 2, 0, negative 1. And I want the eigenvects of matrix A, and I want to print it in a pretty way so that it's easy to read. Okay. And there we go. So the first number, remember, of each one of these sets is an eigenvalue of matrix A. The next number just tells you the multiplicity, how many times it occurs. Okay. So each one of these says that in the characteristic equation, it would only occur once. And then we have the eigenvector associated with that eigenvalue. All right. So matrix D right off, we know is going to be the diagonal matrix with entries equal to the eigenvalues. So negative 3, 0, 3. Just grabbing these eigenvalues here. Right? Now, we learned when we diagonalize a matrix, we could just take the eigenvectors as columns of a matrix P, and then P inverse AP is equal to our diagonal matrix D. All right? But that's not going to work here because we want to make sure that P isn't just any old matrix, it's an orthogonal matrix. So not only do the columns have to be eigenvectors of matrix A, but the columns have to be orthogonal to each other and normalized. They have to be unit vectors. Okay? Now, based on the real spectral theorem, the theorem we just proved, different eigenspaces of a symmetric matrix are going to be orthogonal to each other. So that means, and you could check this vector is going to be orthogonal to this vector, is going to be orthogonal to this vector. They're already orthogonal, all right, because they're coming from different eigenspaces. They are associated with different eigenvalues. What we do need to do, though, is we need to normalize each one of these vectors. All right. So I'm going to take my three vectors, v1, which is negative 1, 1/2, 1, and I'm going to normalize it. And I'm going to call it u1, which will be the unit vector pointing in the direction of v1. And so I will get, so the norm of v1, let's do that first. Norm of v1, I get 1 plus 1/4 plus 1. 1 plus 1/4 plus 1, that's 2 plus 1/4, which is 8/4 plus 1/4, that's going to be 9/4. So that's going to be square root of 9/4 times vector -1, 1/2, 1. Now, of course, square root of 9/4 is equal to 3/2. And so if I multiply that through, I'm going to get -3/2, 3/4, and 3/2. Sorry, I'm dividing. Wrong way. -1 divided by 3/2 is -2/3. -1/2 divided by 3/2 is going to be 1/3. And 1 divided by 3/2 is 2/3. There we go. That's better. Okay. And this is my lambda equals -3 eigenvector. And now it is a normalized vector. It has unit length. I'm going to need to do that for each one of my eigenvectors. All right. So now let's do lambda equals 0. The eigenvector for lambda equals 0, I'll call it V2. That's going to be 1/2 -1, 1. So U2, I just want to be vector V2 normalized. Okay, so I'm normalizing each of these. I want unit eigenvectors. Notice the components in V2 are the same as V1, so the norm will be the same in both. Okay, so 3/2 is the norm of vector V2. 1/2 -1, 1. So I'm going to divide each component by 3/2. 1/2 divided by 3/2 is 1/3. -1 divided by 3/2 is 2/3. 1 divided by 3/2 is, sorry, this would be -2/3. And +1 divided by 3/2 is +2/3. Okay? So I've normalized 2 of my eigenvectors. I have 1 more to go. I have to normalize the eigenvector associated with 3, which is 2, 2, 1. Okay, so now let's do the lambda equals 3 eigenvector. I'll call it V3, which is 2, 2, 1. To get my orthogonal matrix, I'm going to need orthonormal eigenvector, so I need to normalize it. So I'm going to call U3 and the normalized eigenvector that I have here. So I just take my current eigenvector, divide it by its norm. That's going to normalize it, give it unit length. So V3 is 2, 2, 1. And then 2 squared plus 2 squared plus 1 squared is 9. So I get square root of 9. Square root of 9 is 3, right? So I'm going to get 2/3, 2/3, 1/3. Okay? And so put these together, and I will have an orthogonal matrix Q. Now, remember that when you're finding, when you're putting together Q, you need the columns of Q to correspond to your eigenvalues. So since my first eigenvalue is -3 that I've decided to put in matrix D here, my diagonal matrix D, my first column of matrix Q has to be the orthonormal eigenvector corresponding to that eigenvalue. So it has to be U1, because that's going to be the eigenvector corresponding to matrix D. So -2/3, 1/3, 2/3 is my first column for matrix Q. The next eigenvalue I chose to use in matrix D, my diagonal matrix D is 0, so I need to look at the normalized eigenvector corresponding to that eigenvalue. So 1/3, -2/3, 2/3. That's going to be my next column in matrix Q. 1/3, -2/3, 2/3. Okay. And then since my final eigenvalue is 3, I want my final column in matrix Q to be the eigenvector, the unit eigenvector associated with that eigenvalue. So 2/3, 2/3, 1/3. Okay, so there's Q, there's D, and that gives us a answer to this problem. I do want to point out that the answer is not necessarily unique, just like when we did diagonalization more generally. If the entries here in the diagonal matrix have to be the eigenvalues of the matrix, but it doesn't actually matter what order you put them in. I could, for example, swap these two eigenvalues. Okay, but if I do that, I would also have to swap these two columns because I want the eigenvectors in Q to correspond to the eigenvalues in the diagonal matrix D. Right? This is now an orthogonal matrix, and you could check all the rows of Q are orthonormal with each other. All the columns of Q are orthonormal with each other. If you were to calculate Q transpose times Q, you would get the 3 by 3 identity matrix. It is an orthogonal matrix.